Welcome to the first lecture of this practical quantum computing course. At first, let me introduce Qibo. Qibo is an open source framework for quantum computing, which can be used for both implementing classical simulation algorithms and, if you want, for executing your codes directly on the quantum hardware. Anyway, in this course, we are going to take into account just the classical simulation of quantum computers. So, from now on, we are going to speak just about simulation. Let me give you some more information now about Qibo before starting. Diving into Qibo, we have at first a general language API. And this high-level language can be used for both implementing quantum annealing, so adiabatic computation, and quantum circuits approaches. After the high-level language, we have our own implementation of the algorithms, and then the execution can be deployed on different engines. As you already know, we call these engines backends, and we represent them here with this specific symbol here. We have in particular some simulation backends that are the ones on which we are going to focus on. I would like to underline QuTalent and NumPy backends. We also have the possibility to deploy our algorithms directly on the quantum hardware by selecting the QuiboLab backend, which is deputed to control the drivers, convert gates into pulses, and so on. So, this is the macro structure of Qibo, and now we can also have a look to the web page if you want to have more information. As you can see, on the web page you can find many informations. In the main page here, you have some new about the last release of Qibo, some general instruction, also some installation instruction here, and a more detailed version of the diagram you saw before. If you want to dive into Qibo, then you can go directly to some examples, some applications, publications related to the software, and you can have a look to the documentation. In this legend here, you can see that we can go directly to the high-level API documentation for Qibo, or for QuiboLab, that's the backend deputed to deploy the algorithms and the circuit execution directly on the quantum hardware. We have a calibration module, the QuiboJIT, we already mentioned, and so on. So this is a good source of information if you want to have more knowledge about Qibo. So I guess now we can put our hands directly to the code. If you don't have Qibo already installed in your device, I would suggest you to set up a Python environment and then use the pip installer. And we can start by typing pip install Qibo and pip install QuiboJIT. These are the outputs. So now everything is installed. One of the features of Qibo is the modularity. With this I mean that in Qibo you can select the most suitable engine to execute your algorithms. And we are going to call these engines backends. We have backends for both simulation and execution on the real quantum hardware. Two of the simulation backends are NumPy and QuiboJIT, which take their names from two Python packages. But probably you already know NumPy between of them. Note that in this series of lectures we are going to use the QuiboJIT backend in general, which is also the best one when we aim to simulate a large number of qubits. And with large I mean more than 20-25 qubits. Note also that in the lectures we will use the NumPy package itself, which will be used to generate random numbers or to compute mathematics. So I think is everything, and so now it's the moment to put our hands on the code. We can start by importing the packages and the modules we want to use. So we import at first NumPy, and then we also import Qibo and some useful classes and modules from Qibo. circuit, gates, and Hamiltonians. Now that we have Qibo imported, we can set the backend. And we can do this by calling Qibo.setBackend. And in this function, we can set the backend, which is, in this case, QuiboJIT, and the platform. The platform is particularly useful with QuiboJIT and also with the hardware backends, because you can select the engine, so the practical engine you want to use. In this case, we set Numba. Again, if you are using QuiboJIT like us in this moment, you can also set the number of classical nodes of your computer to be used during the simulation. So we can say Qibo.setThreads, and you just type the number of threads. In my case, I will set 16 threads. So this is the moment of building our first Qibo circuit. And we can start by setting the number of qubits. So we set the number of qubits, for example, to 4. It's just an example. Then we can create our circuit by calling the circuit class. So C equal to circuit. And we should set the argument n qubits to be equal to n qubits. Now we have our Qibo circuit, and we can also print it, if you want. With the function circuit.draw. As you can see, the circuit is empty. So the following step is to add some gates. For example, we can add the most famous gate, the Hadamard gate, to the circuit. We can say, for example, circuit.add gates.age, and then you should select the qubit on which you want to apply the gate. So, for example, qubit 0. You can also apply another Hadamard gate to qubit number 1, for example. Then we can add, for example, some Pauli's gates. So C.add gates.z, apply the gain to the target qubit number 2 or 3, it's fine. And then we can apply an X gate to the qubit number 0. Another possibility is the one of building controlled gates. And we can start by building some very simple control gate like the C0 gate. You can say C.add gates.C0, and then you should set the control qubit, let's call it Q0. For example, we can set the number 0, and then the target qubit, Q1, the number 2, for example. We can also add some more complex controlled gate. C.add gates.cz, for example. Q0 equal to 2 and Q1 equal to 1. And finally, I would like to show you some more complex way to build control gates. In particular, you can, thanks to this Qibo circuit method, you can build multi-controlled gates. And you should do that by selecting the gate you want to implement. So typing, for example, C.add gates.y. So in this case, we are applying a y gate to the qubit number 1. And then you set controlled by, and you can list the qubits you want to be the controlled qubit of the gate. So for example, 2 and 3 and 0, let's say. Perfect. So now we have our quantum circuit, and we can visualize some information about the circuit. Let's say C dot summary. We can print it. And then you have some summary of the information of the circuit. The circuit depth, the total number of gates, the number of qubits, and so on. At this point, we can also draw again the circuit. So we call print c.draw, and we print it. As you can see, we have our couple of Adamant gates, the Z here, the X gate, the control NOT, the control Z, and the multi-controlled Y. So this is the way we can build our first circuit in Qibo. When we deal with quantum computers, we have qubits, and each qubit can have two values, 0 and 1. If you combine them together, many qubits, then you can build what you call bit string, so a sequence of zeros and ones. And when you have many qubits together, the number of possible bit strings we can build using this circuit is exponentially growing with the number of qubits. So now we are just going to use a function that we wrote and will return us the complete list of all the possible bit strings given a certain number of qubits. So what we go now is to import that function. We can start by importing from scripts.utils import generate bit strings combinations, and then we can generate the bit strings by calling the function. So generate bit strings combination, and we should provide the number of qubits equal to n qubits. Perfect. So now we have our bit strings combination and we can print it. As you can see, we have all the combinations, all the possible combinations of these 4 bit values here. Going on, we can now execute the circuit we already coded before. And it's simple because you can just type C, open close parentheses. So you call the function and you execute the circuit. As you can see here, what you get is a quantum state, an object of Qibo. If you print it using the Python printing function, you will see the quantum state, which is a certain combination of these 4 possible states here. In particular, we can print, if you want, just the amplitudes. Printing print c dot state. In the amplitudes vector, you will see that some of them are non-zero, the 4 you see here in the explicit formula, and the other one are set to be 0. So now let me collect the final state into an object we call outcome. So now once you have executed your circuit and you collected the results in some object, like in this case we called it outcome, we can, from outcome, compute also the probability values of the amplitudes. So we say outcome dot probabilities, and we can save it into some object like probs, which we can print. As you can see, we have the same bit strings of before, but at this time we have the values of the probability corresponding to each state. And if you want, we can also print it side by side with the bit string value. So we can just do some loop, for example, for e in range len bit strings. So we loop over the bit strings and we can print some string, like probability of state bitstrings OV equal to probability of index E. And as you can see, the only four values that are basically 0.25 are the one corresponding to the amplitudes we already saw in this explicit formula here. So now we can move on by executing some more realistic circuit, adding what we call measurement gates. If you want to simulate a more realistic scenario, then we need to add, in the very end of the circuit, some measurement gates that are going to emulate what happens in a real case scenario. And so that after the execution of the circuit, then you need to perform measurements. And so this will inject some randomicity inside the problem. And for doing this, we can now take the same circuit of before and we reproduce the same structure of the circuit, but adding the measurement gates. So let me at first copy-paste the circuit from the previous source. So the first thing we can do is to initialize a circuit of the same dimensions in terms of qubits of the one we already implemented. So we say C equal to circuit and qubits equal to n qubits, which we set to be 4. Then we should add the same gates of before, so let me go up and we just copy paste them because it's simpler. So copy paste here. Perfect, so now we have the gates, but we are still missing the measurements that we can add here. So c.add gates.m, and then you can refer to all the qubits in this way. So we can say star, range, and n qubits. This will add a number of gates equal to the number of qubits. And finally, we can print the final shape of the circuit. And as you can see, we have the same circuit of before, but now, in the very end, we also have the measurement gates. So what we can do now is to execute the circuit in a slightly different way we did before, in the sense that now we can do the same. We collect an outcome object, executing the circuit, but at this time we add n-shots. The n-shots argument is the one thanks to which we can define how many times we want to simulate the repetition of the circuit execution. And we can set, for example, 1000. We can also have a look to the outcome object, printing it. And as you can see, we still have the exact state simulated. It's the same of before because until this point we have exact simulation. If we want to have access to the probabilities in an exact way, we still can do that. Indeed, we can print as before outcome dot probabilities. And we have the same values of before. Another thing you can do with probabilities is to select some specific qubit of the system. So, for example, you can print outcome dot probabilities, and then you set qubits, and you choose some of the qubits of the system, for example 0 and 3. And you will get a restricted list in which you get just the probabilities of getting the combination of the bits for the qubit 0 and the qubit 3. Or, if we want to exploit the measurements, then we can collect another kind of result, which is called frequencies. And so we call frequencies equal to outcome dot frequencies, and we can print it. As you can see, we get a counter object, which is a dictionary, in which we are collecting each bit string here, and associated to each bit string, we also have the number of times we expect that specific state after the execution of the circuit. The sum of these numbers will be 1000. Now we can visualize the state in a more graphical way, if you want. And also in this case, we already implemented some plotting functions. So let me just importing them from scripts, .plot scripts, import visualize states. Now we already collected the frequencies object, but we can do it in a more explicit way by typing outcome dot frequencies, and now we specify that we want binary equal to true. So we are forcing the Qibo to returning a dictionary in which the keys are the bit strings. And then we can call the function. So visualize state, just passing the frequencies. As you can see from the plot, now we have 4 bars here. Each of them is corresponding to one of the bit strings. And we have the height of the bar is equal to the number of times we got that specific result after executing the circuit 1000 times. Now we can go on and we can see another interesting feature of the Qibo circuits. The next feature we are going to see is how to combine together more than one circuit. And with this I mean circuits that have the same number of qubits. This can be very useful in contexts in which we aim to create a single circuit which is composed of many pieces. Let's take as an example what you see in this cell here. So we already coded here 2 different circuits that we called C1 and C2, which are both circuits of 3 qubits. The first one is composed of 3 gates, the second one of 4, but it's not very important how many gates we have here. It's just to see that we can combine them together. Then we can run this cell and we can print these 2 circuits as you can see here. So we have circuit 1 and circuit 2. Then if you want to combine them together, you can just type C equal to C1 plus C2. And then we can print them. Print C.draw. And as you can see, the final circuit is exactly the combination of circuit 1 and circuit 2. In this first lecture, we had a look to the primitives of Qibo. We understood how to define our first quantum circuit, adding the first gates, and so on. Now, in the next lecture, we are going to put this into practice by implementing some more practical examples.